So right now I want to talk about section 3.2, which is about the factor and remainder theorems. So suggested exercises are 1, 3, 21, 23, and 31. Now the big thing, which you've already seen, is going to be long division for polynomials. And then we're also going to see the factor and remainder theorems. I guess this is... All right, so theorem 1, and I'm just going to put this in here. I guess I don't need to write theorem 1. I'm just going to make this, this is a theorem, but it's got a funny name. The name is the division algorithm. And I don't really know for sure, but what I've been told is that the division algorithm was given its name before we really had a good hold as a species on what the words theorem or algorithm meant. So it's that old, and that's what I've been told. Now, who knows how accurate that is? But this is mainly just going to give us some language. So if f, the dividend, and p, the divisor, I guess I'm defining these, are polynomials, then whenever p does not equal 0, well, p of x does not equal 0. So for whichever x, p of x doesn't equal 0, there exist unique, and this is the big part of this, there exist unique polynomials q, which is called the quotient, and r, which is called the remainder, such that, and here's, this has been called the division algorithm, and we're so excited to see the division, such that f of x equals p of x times q of x plus r of x. All right, yay. So division algorithm, not an algorithm, also doesn't have any division in it. Great name. Okay, so this as written doesn't appear to have division in it, but if you think of it as f divided by p is q plus some remainder, which would be r over p in this case, then you get exactly the long division that we already did earlier in the class. So this is the key thing here. I'm probably not going to be examining you too much on this particular theorem, so much as I just want you to be aware of the words dividend, divisor, quotient, remainder. So the big idea here is that we can run division on polynomials the same way that we did division on, with numbers. So let me do, again, some polynomial long division. So just, we've already seen this. I hope you're starting to see a pattern here that I've touched on a lot of this in our review because it's review for many people. And so for the people for whom it's review, it's old hat. The people for whom it's not review, hopefully now that you've seen it once, you're like, oh yeah, I've messed with that before, and hopefully it's not so scary. Okay, so what I want to do is I want to compute x cubed minus 2x, plus 2x minus 3 divided by x plus 1. All right, so how do we do this? Again, we put x plus 1 outside of the house. We put x cubed plus 0x squared plus 2x minus 3 outside of the house, inside of the house, and then we divide. So how many times does x plus 1 go into x cubed? It goes in there x squared times, so I get x cubed plus x squared. I subtract, and I get negative x squared. Drop down the 2x. How many times does x go into negative x squared? It goes in there minus x times. So I've got minus x squared minus x. Subtract. Now, negative x squared minus a negative x squared gives me 0. So I've got 2x minus a negative x, leaving me with 3x minus 3. Oh, sorry. Forgot that. So how many times does x go into 3x? Well, it goes in there 3 times. So I have 3x plus 3. And when I subtract, I'm left with, of course, negative 3 minus positive 3, so I'm left with negative 6. So the remainder is negative 6. So we can write it like that. We can also write, if we want to write this using the division algorithm, we would write x cubed plus 2x minus 3. Oh, this is the final answer. This is when I said compute. But what we just discovered, the relationship that we just showed, was x squared plus 2x minus 3 is equal to what? It's equal to no. Okay, I got off by a line, but it's all right. Is equal to x squared minus x plus 3 times x plus 1 minus 6. Okay? So that is to say, if I divided both sides by x plus 1, I would get this thing up here. So this is just seeing the division algorithm in action. Basically, the division algorithm, the big part of it is it says that this and this are unique. Moreover, I should say the degree of r is strictly less than the degree of, I don't know if I have this in the notes here. Yeah, degree is strictly less than p. Okay, I forgot to write it down. This goes in this theorem. It is in my notes, though. I was just making sure I hadn't made a mistake in my notes as well. So this basically says that when I run this division algorithm, when I do this process of long division, I get the same answer every time. That's essentially what this theorem is telling us. It's not like I could go through this process here and get 2 different answers. Right? Okay. So that's kind of review. If not, definitely take a look at that. So let's move on. So what I'm going to do is I'm going to state 2 theorems, and they're basically, one of them's a special case of the other. So first, let's do the remainder theorem. And the remainder theorem just says, if p is a polynomial of degree at least 1, and c is a real number, then when p is divided by x minus c, this binomial, the remainder is p of c. Okay, so the remainder meaning like this remainder here. Okay, like what we computed in the last example. So let's do an example of this. So let's let p of x equal x squared plus 3x plus 19. And let's compute p of 1 2 ways. First, by plugging in, and second, by using the remainder theorem. Okay, so the basic idea is solution. To do the first one, well, p of x is x squared plus 3x plus 19. And that means that p of 1 is just going to be 1 squared plus 3 times 1 plus 19, which is 23. Okay, not that interesting, not that exciting. It's evaluating a polynomial. So that was solution number 1. Solution number 2 is going to say that we can figure out what P of 1 was by going through way more work. Okay? And if you're wondering, wait, why would I want to do way more work? I just proved this in literally one line, or I just computed this in literally one line. Why would I want to do more work? Right now I'm just trying to demonstrate that the remainder theorem works. Occasionally, you might show up with a different polynomial, and it'll actually be easier to do the division than to do the than to compute it. I doubt that's going to happen in many natural consequences, but it's possible. And I really just want you to see that the remainder theorem indeed works, so that we can move on and do the next thing. But first, let's just do this. So to compute P of 1, what I need to do is so I'll write this: to compute P of 1 with the remainder theorem, I need to divide P of x by x minus 1. So to compute P of c, I need to divide by x minus c. So we write the P of x inside the house, and make sure to leave space above the house. So inside the house, we write x squared plus 3x plus 19, and outside the house, we put x minus 1. All right, how many times does x go into x squared? It goes in there x times, so I've got x squared minus x. I subtract. I'm left with 4x plus 19. How many times does x go into 4x? Well, 4 times. And so I've got 4x minus 4. And when I subtract, I have a remainder of 23. Just as claimed, 23 is exactly P of 1. Now, most of the time, you're going to see this is more work than just plugging into the function. But occasionally, you don't know how to evaluate the function quickly, and occasionally you're just given information like the remainder. Again, this is knowing the remainders of things is more often seen in like a computer science context. So I don't want to go too far into this, but let me just say the remainder theorem works. I haven't proved it, but I've given you an example where the remainder theorem works. Okay? So let me state the factor theorem, and then you're going to see that it's a special case of the remainder theorem. So the factor theorem just says, suppose P is a non-zero polynomial of degree at least 1. Then what do we say? We're going to say C is, whoops, I didn't tell you. The real number C is a 0 of P of x if and only if, remember IFF means if and only if, x minus C is a factor of P of x. I'll just remind you, this means if, oh dear, that was weird. Bump the home button and then I tap the screen. If and only if. That's what IFF means. So why should we believe this? Well, the factor theorem is just the remainder theorem when the remainder is 0. So, aka remainder theorem with a special case that P of C equals 0. So it's not really that surprising. It's just that a lot of times when we use the remainder theorem, we're going to be calling it the factor theorem. We're going to be using this special case of it called the factor theorem. Okay, so let's do an example so you can see what I mean. Let's let P of x be x squared plus 3x plus 2. And I want to verify, is that like a werewolf bites you and verifies you? Verify that negative 2 is a root of P of x 2 ways. And again, 1, plug in, and 2 by the factor theorem. Okay, so solution. So first, let's just plug in -2. So p of x, as we said, was going to be x squared plus 3x plus 2. And that means that p of -2 is just -2 quantity squared plus 3 times the -2 plus 2. And if we add all this together, what do we get? Well, we get 4 minus 6 plus 2, and that's 0. Ding, 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 ding. So we get that it is a 0. So here's solution 1. Solution 2, let's use the factor theorem. So let's divide x squared plus 3x plus 2. We're going to divide that by x minus c, or x plus 2, because we're doing x minus a -2. So how many times does x go into x squared? It goes in there x times. So I get x squared plus 2x, and I subtract. And x squared minus x squared is 0. 3x minus 2x leaves me with x. Drop down my 2, so I get x plus 2. How many times does x plus 2 go into x plus 2? Well, exactly 1 time. So I'm subtracting off x plus 2, and that gives me a remainder of 0. Okay? And what that means, if I divide two things and there's a remainder of 0, that means precisely that this was a factor, that this divisor was a factor. Okay, and let's externally check that. So here the remainder is 0. Let's just check that x plus 2 times x plus 1 is indeed x squared plus 3x plus 2. If we FOIL it, we get x squared plus the outer, so plus x, plus the inner, plus 2x, plus the last, plus 2. So x squared plus 3x plus 2 was indeed x plus 2 times x plus 1, which means that x plus 2 was a factor of the original polynomial. So hopefully that made sense. And again, hopefully what happened made sense. If why we go through all those hoops to just get what we could have gotten with one line of plugging in. If the why isn't entirely clear, that's okay. I just want you to see that this does indeed work, and then the whys can come later. All right. So sorry for that.